Hi, welcome. We have completed 2 modules so far. The first one is matrix algebra, and the second one we look at the optimization. In these 2 previous modules, we examine other people's models built by scientists and engineers. The third module, we're going to learn how to build our own models based on what we learned in this course. So in this lesson, we are going to give an overview about what's the next 12 hours of this module. And we look for model classification and the modeling process and the methodology. So as an overview, we have these 4 components. First, we look about the purpose of mathematics modeling, and then we look at all different models, how we classify those models. And then after this, we look at the modeling tools and the methodologies. We only introduce 3 of them. And finally, we're going to introduce the process with emphasis in verification and validation. So how about start with a few questions like this. So if I ask you, how would you like to describe the solar system and the motions of the planets, and how you're going to do it? Well, it depends the time frame and how much pages I give to you, and you can put your hand on to start writing down what you think is important. And second, I ask you, how would you like to describe the traffic light? Just think about the traffic light in the corner of the busiest street in your location. And also think about how would you like to model your own learning process to evaluate your learning about the information, knowledge, expertise over a month, year, or a lifetime. Well, you can start to describe all those qualitatively, to think of what factors you have to consider, and then try to think quantitatively how you're going to count, measure, and evaluate all those facts. Well, the question just to bring you to this big gap between the real-world applications. You really get the problem right in English or any natural language. On the other end, you need to translate those critical components into the mathematics language. And here, if you learn the differential equation, we call it second order ODE, with the initial condition and the Dirac delta function. So our focus on mathematics modeling is on the big gap between the real-world problem and the problem in your textbook. So let's start from the traditional science. Traditional science have theory, of course, and experiment. And whatever we defined as a hard science, like physical science, chemical science, chemistry, and if you say you have a theorem, you need to either prove it in mathematics language, or you can repeat what you claimed in the laboratory by experiment. But in the modern history, with the advance of computers, we got the third leg of the science. That third leg is called computational. Just like what we did right now, simulation, modeling, that's part of the computation. In a lot of situations, you neither can prove nor to experiment it. So what you're going to do, use the computer to simulate the phenomenon. So this course, by the way, is also titled as Introduction of Computational Science. Our focus is on the third leg of science. So when talk about computation, you always have to associate with these two words, a model and a system. And these two words are really the flip side of the coin. So you call it dual concepts. And they are so fundamental, we can describe what is a model and what is a system, but we really lack of a fundamental definition. In the same way, it's hard for us to define what is a straight line. You can know what is a straight line, but we don't have a definition for it. So we can start from a system. A system always associated with a hypothetic boundary of the problem. That means you assume some condition. Under that condition, you are going to investigate the problem. And that hypothetical environment condition, regardless of given explicitly or implicitly, it must be there to help you focus on the problem and the concern, what you really need to concern. So let's just give a little example to explain that the hypothetic boundary later on. So any system, it could be made of multiple subsystems. You can call it the child systems. And this subsystem, there are systems themselves. And they can also have subsystems, and they can have either one or two or multiple parental systems, or we call it super systems. Now, give an example. When I consider autonomous underwater vehicle, AUV, as a system, the AUV have communication subsystems. And these communication subsystems have also its own subsystem, like a wireless communication by Wi-Fi or acoustic subsystem. So you have a whole hierarchy of a system. The AUV system could belong to itself in a fleet with the ground station, and so you have to use this word recursively in systems. So now the next, you're going to see I introduce a whole hierarchical structure of the model, from the scientific model to mathematics model to particular type of mathematical models. In a similar way, like you look at the Google Earth, you start from the whole Earth, you zoom in, down, and look at all detail. So what is a scientific model? Well, a scientific model is an artifact in the scientific research. It's the language you choose or the material you choose to represent the essence relevant to what you concern, to a particular perspective, or you can call it a view, what you really wanted to look. Now, give an example. You can look at all different types of maps, a geographic map, a road map, and you can look at the blueprint of an architecture, and we can look at ordinary differential equations, mostly in this course. So you really have a relativity of the essential and the non-essential factors. Now, what it means essential and non-essential? Now, if you consider a geographic map and you could not find a major highway, you don't count. This is a defect of the model, because geographic map mostly think about the river, the mountain, the feature of the geography. However, if you are going to think about a road map, you cannot find the major highway I-95, that's a big defect. So it really depends what you really consider in the problem. Give you another example. If I want to experiment the falling solid object in a closed lab, so you use Newton's law and you make an assumption to neglect the air resistance. Fine, that's how we do it. And you are going to consider the G, the gravitation, equal 9.81 meter per second square. Perfect. However, if you want to consider to design a parachute, and you make the same assumption, you say let's neglect the air resistance. That's a fundamental flaw, because the air resistance is an essence in this model. So we talked about a scientific model. Now, what is a mathematics model? Well, any scientific model, if you express in mathematics language, it's a mathematics model. Be honest, it's hard to find any scientific model is not represented in the mathematics language. That's just to show your field is still too immature, shallow. So mathematics model, you can think about functions, differential equations, graphs, state machines. So what is the difference between mathematics model or mathematics as a language? Well, it distinguishes itself from natural language by its accuracy, preciseness, and the conciseness. The preciseness requires this language be refutable. What means refutable? Means require your answer, if it's a logic problem, either yes, right, or no. That's refutable. If you're wrong, should have a way to find it. Second, cannot be ambiguous. That means each term you define should have no second interpretation, like in the other end political science.